Good day, everyone. So, what we are going to be talking about today is derivation of ODEs. We are going to derive ODEs from any given equation. So, derive ODEs from the following functions. We have five functions here, and we need to derive ODEs from each and every one of them. So, there's one thing I would like you to know first before we continue. Anytime you see a function and you're asked to differentiate and you're asked to derive an ODE, so the first thing you need to check is how many constants are in that equation, in that function. The amount of constants, arbitrary constants in that function determines the order and the time number of times you have to differentiate. For example, look at this. We have only one arbitrary constant, right? That means we are going to differentiate once, and this will yield the first order ODE. We have three arbitrary constants in this, right? So this means we are differentiating twice, and we will have a third order ODE. For this, we have two arbitrary constants. We don't need this one as in the sense of arbitrary constants, we don't count this one as arbitrary constants. Please note that. So we have only two arbitrary constants in this function, which means we are differentiating twice, and we will have a second order ODE. For this, we have only one, differentiate once, first order. For this, we have three, differentiate thrice, and this is the third order ODE, right? So now let's start with the first one. Y equals to ax. We are differentiating once because it's the first order ODE. We have only one arbitrary constant we are differentiating once. Y prime equals to a. So what do? I have to compare both of them. Then in my b, I have to eliminate the constant a. Forming ODEs is all about eliminating the constants. Eliminating the constant. So anywhere I can compare both and just use this. And I say anywhere I see A, I replace with y prime. So I have y equals to, instead of writing A now, I write y prime x. And that's all. But I can rearrange this to form a better ODE and say x y prime, right? Rearrange x y prime. I can bring this to the other side and say minus y equals to 0. And this is my final ODE. That's all. Going to the second one, I have y equals to ax squared plus bx plus c. So this is a third order ODE, right? What I'm going to get out of this will be a third order ODE. So I differentiate this thrice. The first derivative give me 2ax plus b, the second 2a, and the third 0. So basically, what I have here is a third order ODE, and this will be my final answer. This will be my final answer. I don't need to substitute anything. No, since my final ODE is 0, this is going to be 0. Because the real reason is because of this. This is a polynomial. This is a polynomial. If you have something like y equals to ax plus b, when you differentiate this is going to give us only two, the second order equation, right? Y prime equals to a and y double prime equals to 0. So since it is a polynomial, this is also what you're going to get. The second order equals to 0, right? That's all. So going to the third question, we have y equals to a sine ax plus b cos ax. So this has two arbitrary constants, which means I'm differentiating twice. The first derivative give me y prime equals to, this is sine. When I differentiate sine, I get cos, right? A is a constant, a cos ax. Now, since it is a function of a function, I differentiate what is inside of it, which is a times a plus b. Now I'm differentiating cos, I'm getting sine, which means minus b sine ax times a when I differentiate what is inside. So my y prime will be a cos ax minus ba sine ax. This is my first derivative. Now my second derivative will be, I'm differentiating cos, which means the negative will be outside, minus a is coming out again, a squared sine ax minus b, a is coming out again, right? Cos ax. I've differentiated the second time, so I'm not differentiating anymore. Now I can easily factorize a squared and negative out of both sides. So I have y double prime equals to minus a squared into bracket. I have a sine ax plus b cos ax, right? So since I want to eliminate this a and b, what do? I compare this to my first derivative. They don't really look much alike. I compare it to my first derivative, and what you notice is that a sin ax plus b cos ax, they are basically the same thing. So everything that is inside this bracket is the same thing as my initial function y. Do you get? So I'm just going to rewrite this as y double prime equals to minus a squared y, and that's my final ODE. There's no more constant in this equation. I can now bring this to the right side if I wish. Y double prime plus a squared y equals to 0, and I'll call this my final ODE, the second order ODE, and that's all for the third question. Now, going to the fourth, I have y equals to x plus a over x. Now I can write this as y equals to x plus a x minus 1, right? Yeah. I have only one constant, which means I'm differentiating only once, and I'm going to get a first order derivative. So my first derivative gives me 1 minus, right? Since this is coming down, minus ax minus 2. So what do? I try to make a the subject of the formula in this. So I have a x minus 2 by bringing this to the other side, and I'm bringing this to the other side too. 1 minus y prime, right? I've brought this here and brought this here. So I can now multiply through by x squared. Multiply through by x squared. Why am I doing this? I want a to stand alone. So I have a x minus 2 x squared equals to x squared into bracket 1 minus y prime, right? Log of indices 2 minus 2, that's 0, right? X raised to power 0 is 1. So I have a equals to x squared. I'm opening the bracket now. X squared minus x squared y prime, right? Now, what I am using this for is so I can substitute into the original equation, the original function, so as to eliminate a. So if I bring this into this original function, I have y equals to x plus, instead of writing a, I write all this, x squared minus x squared y prime over x, right? I can now simplify this into y equals to x plus, x can easily cancel the squares on top, right? Yeah. Plus x minus xy prime. So this is the same thing as writing 2x minus xy prime. Now I can rearrange this ODE and write, when minus xy comes to the other side, it becomes xy prime. There's y here already, plus y equals to, I have 2x on this side, equals to 2x. And this is my final ODE. And that's all about this. So going to the last but not the least, going to the last but not the least, we have y equals to c1 e raised to power x plus c2 e raised to power 2x plus c3 e raised to power 3x. Now this looks like the characteristic solution of the ODE of a, what should I call it, of a third order ODE. So we are just going to say, looking at this, e raised to power x can function as r equals to 1, right? If y equals to e raised to power rx, it means our r equals to 1 in this. Using this format, y equals to e raised to power x. We are going to learn more about this when we enter second order ODE, solving something like this, y double prime plus y prime plus y equals to 0. And we are asked to find the characteristic solution of this. We are going to learn more about this. So solving this, we are going to use y equals to e raised to power rx. And looking at e raised to power x, we can see our r is 1. Looking at e raised to power 2x, we can see that our r equals to 2 here, right? And looking at this one, we can see that e raised to power 3x, our r equals to 3, right? So basically, that means the solution of this kind of ODE means r minus 1. From here, if we bring this to the other side, r minus 1 equals to 0, right? For this one, r minus 2 equals to 0. And for this, r minus 3 equals to 0. So I can just pack everything together and turn it into a cubic equation. R minus 1, r minus 2, r minus 3. This is basically the operator D method. Yeah, it's basically the operator D method. I can turn this into D instead of R. I can just turn it into D. d minus 1, d minus 2, d minus 3 equals to 0. I can add 1 here. So now, opening this bracket, I have d squared minus 2d minus d, that gives me minus 3d plus 2, right? And d minus 3 equals to 0. Opening this again, we have d cubed minus 3d squared minus 3d squared. So this gives me minus 6d squared, yeah, plus 2d minus 9d minus 6 all into bracket y equals to 0. So once I finish this up, I have d squared, d cubed, sorry, minus 6d squared minus 7d minus 6 y equals to 0. So I can now open this. Now, there's something you have to note about ODEs. If I have something like this, dy, it means y prime. If I have that squared, it means y double prime. If I have the cube y, it means y triple prime. So this, if I open this kind of bracket, I have the cube, right? So this means y triple prime minus 6y double prime squared minus 7y prime minus 6y equals to 0. So this is the ODE that is going to be formed once I finish this differentiation. Once I finish opening this bracket, and this is our ODE from this type of equation. But there's another way to solving this, which you can actually try out. There's another way to solving this, which is by eliminating the constants. So let's try it out. It's basically the methods we've been using before. So we are going to differentiate these thrice. The first derivative gives us c1 e raised power x plus 2c2 e raised power 2x plus 3c3, yes, e raised power 3x, right? The second derivative gives us c1 e raised power x plus 4c2 e raised power 2x plus 9c3 e raised power 3x, right? Now the third derivative gives us c1 e raised power x plus 8c2 e raised power 2x plus 27c3 e raised power 3x. One reason why I don't like this method is because it is quite long and it might confuse you at some point. So now let's finish it off. We have to eliminate constants. We have to eliminate constants. So what do? We subtract y triple prime minus y double prime equals to, you will see that c1 is very easy to eliminate using this method. So this is gone. 8 minus this gives us 4c2 e raised power 2x, right? 27 minus this gives us plus 18, right? 18 c3 e raised power 3x. So we have something like this on ground. So subtracting y2 and y1 again, we have something like c1 is gone again. 4 minus 2, we have 2. 2c2 e raised power 2x, right? Plus 6c3 e raised power 3x. Then we can still use this again and say y1 minus y itself. Eliminated again. So we have c2 e raised power 2x. 3 minus 1 is 2 plus 2c3 e raised power 3x. So I still have to use other methods to make sure I eliminate all the constants within these equations. I have to continue my elimination method. So what do I do now? I can easily see that if I multiply this one 2 by 2, I can eliminate c2, right? And if I multiply this one 2 by 2, I can still eliminate c2. So I will come down to just two equations. So I have something like this now. Y double prime minus y prime minus 2 of this minus 2y prime minus y will give me something like 2c minus 2c2 eliminated. 6 minus these 2 will give me 4, right? So that would be, oh, we multiply 2 by 2, 4. 6 minus 4 gives me 2. 2c3 e raised power 3x, right? Yes. So if I multiply this one 2 by 2, I'm going to have 4 here. So it means 2 of this equals to 4 of this and 12 of this, right? So I can easily subtract these 2 and just write it out as y triple prime minus y double prime minus 2y double prime minus y prime equals to If I subtract these two, I get this gone up, and this gives me 6c3 e raised power 3x, right? Now I'm down to c3, right? So it remains only one constant. So I can also multiply this one through by 3. So if I multiply this one through by 3, I have 6. And here I'm going to have 3 for everything, right? So if I subtract both equations, I'm going to be down to, okay, just make sure that my y cube is the one on top. So I'm going to subtract this one from this one. Or I'm going to subtract this one from this one rather. So I'm going to have something like y triple prime minus y double prime minus 2 into bracket y double prime minus y prime. Now all this one minus this minus 3 y double prime minus y prime minus 2 into bracket y prime minus y equals to basically equals to 0, right? So after everything now, I've been able to eliminate all the constants within this ODE, right? So now let me open my ODE and simplify the final thing. So I'm going to have y triple prime. Now for y double prime, I have 1 here, I have 2 here, okay, minus y double prime minus 2y double prime plus 2y prime. Now let me open this one, minus 3y double prime plus 3y prime plus 6y prime minus and plus plus 6y equals to 0. Now let me simplify this, and that will be the end of the y triple prime minus y double prime minus 2y plus minus 3y double prime. So minus times this gives us plus. So when we open this gives us plus, yeah. Minus plus, oh, sorry. Minus times plus is minus already. Then we open this, it turns to minus again. So now let's simplify this. We have only one y triple prime minus 3, right? Minus 6, and that's all. So we have minus 6y double prime. For our first y prime, plus 2 plus 3, that's 5. 5 minus 6. Oh, okay. So y prime, sorry. 2 plus 3, that gives us 5 plus 6, that is 11. Plus 11y prime, and our final minus 6y equals to 0. And this is our final ODE. And that's all about deriving ODEs. Thank you. Like and subscribe.